Okay, can you see the slide? I think so.
Yes,
yes.
yes.
Perfect. Okay, so the current roadmap of the project is this one. So this is the starting of the first year. Okay, next target will be the opening of the Odino project, the Odino laboratory, which is related to the didactics for youngest people. And then we will plan to complete the ICE laboratory by the mid of this year. We just reached the first technical target, and we have to reach the second technical target by the end of this year. The financial scheme of the project is still going very well, because starting from the initial funding that you can see on the left related to the funding that we received from the Ministry of the Research, we had some funding coming from European projects and also some other coming from regional projects, all related to the production of system and all related to the manufacturing, innovative manufacturing of systems. Here there is, for example, the list of companies that we just involved in project, in funded project in the past 2 years. With respect to the educational project, we just arrived the last October to the start of our master degree. The master degree will cover and is covering all the entire software stack from the production plant up to the cloud. And it is based on the idea to produce 3 different professional different fields. And the first one is related to industrial IoT and robotics system designer, the second one on industrial system integration, and the third one about the production programmer and analyst. You can find in the specific, I'm telling this to our reviewers, you can find the specific presentation, the correlation between all the courses that we plan to give and we are providing to our students, and the different part of the ICE laboratory. So we succeeded to identify the contribution, the technical contribution, the practical contribution, and the theoretical contribution of each course with respect to the project. And you can see this in the specific presentation. I have no time now, but in the case you can ask questions also in the future. With respect to the dissemination, we are making some presentation, even if the last year has been not fantastic from this point of view, obviously, but we succeeded to make the formal opening in presence with more than 150 people here involved and looking through the laboratory to all our production plant. And we also open a website, a specific website and a specific YouTube channel where you can find a lot of videos that we recorded about our activities. Okay, but if we go to the specific technical part, that is to the design of the ICE Industrial Computer Engineering Laboratory, let me recall that we started from some hypotheses. The main hypothesis is that we need to focus on small personalized batches for different clients, for different customers. And this need to implement some technologies. In particular, we need to expand the ideas of digital shadow, the digital twin. This has been one of the research direction. We have to expand the possibility to have a production plant which can be dynamically reconfigured. And starting from these 2 technological bases, we can arrive to have a predictive analysis of the plant in order to allow reconfiguration. In other words, okay, we are building this laboratory with the goal of having a completely reconfigurable production line able to learn how to produce a good. This was the target that you gave us during the workshop last year, or better, 1 year and 1.5 ago in December, when you told us that we needed to identify an important target, and this was the target that you indicated. To arrive to this target, we need to reach 3 intermediate targets. The first one was the target of 2020, that is to arrive to have a completely reconfigurable production line, and you will see in the demo that we reached it. then the target, the sub-target, intermediate target of this ER will be the possibility to create a receipt by starting to decompose images, that is, by providing images of the good and by decomposing the images automatically and then to produce it. And finally, the final target at the end of next year will be the creation of receipts and their implementation by recognizing human operations. That is, show to the production line what you would like to obtain by assembling pieces, and then the production line must be able to reconfigure it and to produce it. To arrive to these results, obviously, we started from some industrial implementation and some already developed stuff. This is a list of the providers, and this is the general view of our laboratory, of the HICE lab. All the part of this HICE lab has been identified by a number. These numbers are important for the review because you can find such numbers in the description of all the courses of the exams of the master degree, and also in all the presentation that we will give in the next 2 hours, because each of the presentation we see with this activity I contributed to a specific part number 9 or part number 2 or so on. So we tried to focus all our attention and to cooperate together in order to arrive to this final design. To better clarify this picture, from 1 to 9, there are all the actual parts of the laboratory, that is all the machineries, the hardware machineries, and from 9 to 17, there are all the software layers. So we have a lot of software layers on top of this hardware part. We will go in depth during all the technical presentation, and then you will see in a couple of minutes, you will see the demo. In particular, the demo will show you the network infrastructure, also the possibility that we have to allow to mix IoT and industrial IoT to arrive to capture and to collect data coming from the building and from the production line, and to collect them into an infrastructure that we build on top of Kubernetes in order to arrive to a set of data which are displayed and which are stored on top of a cloud, and also on the simulation, the different simulation models that we have, that is the different digital twins. Okay, this is the introduction. And I will give now the control to all our guys in the laboratory that will show you directly the demo that we can obtain with the current plan. So I don't know if Marco or Carlo, Roberta, Alessia, who will take the phone.
Okay, welcome again to the HICE laboratory. Here you can see the actual status of our laboratory. You can find the warehouse, which is where we store the parts. The mobile robots, one is integrated with our demos. The second is still in progress. Then we have the quality control box, where we are integrating more cameras to give a geometry control of our recipes. Then there is the robotics station, where we move our parts and in future assemble and disassemble parts.
Okay.
Okay. Then we have the 3D printing station with 2 3D printers. The first one is based on stereolithography. The second one is based on the PolyJet printing system. The first one, it's a printer which works with one material at a time. The second one can produce colored parts and parts with material mixed together. Then we have the upcoming milling machine, which is expected to be here in a couple of months. And then the last one is a flying probe tester, or electronic board testing. It's expected to be here at the end of 2021. Then, surrounding this, there is the transport line, which is based on a mini pallet transport system, which it's the primary transport system of the laboratory. The mobile robots has this system, or can overcome this system in the future. Then we can see the digital twin of the laboratory. I share the screen of the main computer. Okay, here you can find the online version of the digital twin, which replicates what is happening to the line. Then we have some dashboards. This one is for the cloud version of the system, which is based on Siemens MindSphere. You can see, in this case, the IoT data coming from the various the sensor in the room, in our laboratory, and in our study. Then we have a version of dashboard which is based upon our data collection architecture, and the same data that we can gather directly from the time series database. Then we have the same dashboard I see you some seconds ago, but this one is directly powered from the OPC-UA data that are flown through the IoT gateway. Then we have another dashboard which is based on OPC-UA, that is gather data from the production line and shows the status of the line in real time. And then this one of the other dashboard that you've seen previously. I close the screen sharing, and I show you what the demo actually does. We have some Lego pieces that we put in a precise position, the outer position of the pallet, based on an external recipe that is automatically generated by our control architecture. Then the pallet with the assembled recipes flows to the quality control check, where we can check if the two Lego parts are put in the expected position, and if they are two good pieces, or one or two is marked as faulty. A faulty piece is a piece where one of the Lego dots is closed. This one is a valid recipes, and the results of the quality check enables to out possibilities for our pieces. These recipes, it's okay, so it stores the two parts, which for us are two final parts, to the warehouse. If the two parts were rejected by the recipes, they go to the waste bin, which is in another location of the laboratory. You can see that when the mobile robot is still operating, we can substitute its function with a human at runtime. that is what happened a moment before. The production line is quite flexible because we have a great ability to parameterize its function, and there are no programs that are started locally. They are all started remotely with the parameters from a minimus that we are implementing on our cloud architecture. And the line doesn't have a single routing, but can support multiple routings, and they can in the future be, how can I say, extended and controlled by an external supervisor, so we can substitute its behavior. I think I have
okay,
I
Carlo,
explain everything.
Carlo, frankly speaking, I think that we can also underline one important point, that is there is not a specific receipt which is implemented by the production line, but dynamically our manufacturing execution system can dynamically select, identify a new receipt. And when the new receipt must be implemented, it is implemented by looking at the status of the production line, where are the pieces of Lego and which are available, which not, and dynamically the new receipt is implemented. This allows to continue to change the receipt and to arrive to the reconfiguration, the complete reconfiguration that we wanted to achieve by the end of last year, which is the basis for the basic level for implementing the future implementation, when we will obtain the receipt by looking as manual movements or by looking at the images. So this target to have a completely inflexible configurable line has been reached, and all the movements that you are looking now has been not predetermined, but they depend on the fact that the random generator of the production line the receipt decided to implement a new receipt, and the implementation at the moment is due to the status of the production line in such a moment. So all that you are seeing now has been reconfigured and implemented, deployed on the machine during the demo itself. So if you will start the demo, you will see a completely different story, because this depends on the random selection of the receipt. Okay. So Carlo, if you want to continue with the show?
Oh, okay, there are, I think, some little things I can show you that now
okay,
we have
implemented. From one moment, Carlo, there is a question from Samajit.
Yes.
Okay.
Yeah. I just had a quick question. So firstly, the demo and the setup looks very, very impressive. But the question I have is, currently this is implementing something like, with these Lego blocks. And my question is that in terms of the reconfiguration and what this production line can do, are there some limitations in terms of what kind of production this is currently restricted to? So for example, if somebody would like to create a part where something needs to be drilled or something needs to be glued together, can some production corresponding to that be implemented, or is it like currently we are operating only in a certain boundary in terms of assembling Lego pieces?
It is a very good question, and our degree of freedom will be given by the 3D printers and the milling machine to produce something which is not exactly a predefined Lego piece, which is in the vertical storage. So if we will produce something which is not a simple composition of predefined pieces, but which require extra pieces, they will be generated. The only problem of generating such pieces during the demo is that the timing of a 3D printer is completely uncomparable with the timing of the other stuff. On the contrary, the timing of the milling machine would be, I think, compatible. So now we will introduce during the next month the mini machine, and the main problems will be the automatic loading of the piece of plastic and the automatic exit of the final piece that we have to do by using the mobile robot. And this is what we are doing. And as soon as it will be ready, we will show a demo in which pieces are not so standard, but they start also from the outside the standard production. And another part that we are expanding is the assembling part. At the moment, the two robots has been programmed by using their own language. And their own language, since they are of different brands, means that you cannot perform a cooperating activity without working with two different languages and so on. What we are doing is to work at the level of the PLC, which connect the two machines, and we are expanding all the basic movements of the two robots, and those we will be able to program the cooperating activity of the two robots, and this should produce a nice composition, because one robot will take one piece, for example, the other one will put another piece on top of it. This is current activity too.
Yeah, thank you. Thank you very much.
Yeah. I have one question, Franco.
Yeah.
So it's very good to see that there is a big progress in IC lab and also your master program. In terms of flexibility in this line, when you change the product, are the robots able to program by themselves, or you have to? Yeah, how much automation is there in terms of robot programming?
This is a very good question. At the moment, the basic operation of each robot is a list of basic operation, and the composition of this basic operation is composed into the receipt. So the receipt is the collection of the basic operation that all the different receipts have been predefined. So the degree of freedom is to jump from one receipt to another, but all the receipts must be manually implemented by the engineer, which is the production engineer. If we would like to reach the target of this year, which is the composition of an object starting from an image, we have also to automatically identify the list of basic operations to compose the final object. And those, in this case, we need to add this smart part, which is start from an image and identify the list of the sequence of operation. And then as soon as there is the list of operation, we go back to the current situation.
Okay, thank you. It's also nice to see that you implemented a digital twin. But is it also the digital twin is able to evolve itself?
Yes.
I mean, with the evolution or the aging of this system or whatever. Yeah.
This is a very good question. Yes, it is. In fact, at the moment, what there is in the demo is a digital schedule. So is the simulation, and data comes directly from the plant. And coming from the plant, the digital schedule reorganizes itself by, for example, positioning all the mini pallet in the correct position with the correct object. If, for example, you take by hand one mini pallet in one position and you move it manually to another position, the current digital schedule reorganizes itself and realign with the standard situation. The skeleton of the digital schedule is fixed. That is, it is composed of the different machines, and all the different machines are in a correct position, and there is not a dynamic generation of digital schedule, but there is a dynamic reconfiguration of it as soon as we change the receipt and we change all the objects which go through the mini pallet belt.
Okay, thank you. Yeah.
Okay, I don't know if there are other questions about the current implementation. If there are not, or eventually, if you have questions, that you can also provide questions during the technical presentation. So in this case, we will go back to the technical presentations, and let me take again the control. This is the summary of all the competencies which has been implemented in this year to obtain what you just saw in the demo. Okay, we subdivide all such competencies into sub-targets. The first sub-target is about system synthesis and verification. Then there is the part related to data and process modeling, and the final part related to all the applications. So now you will see 14 presentations. Each one is for each competence. And so let me give the speech to the first presentation, verification and synthesis of discrete analysis system. If I'm not wrong, is Tiziano Villa. Tiziano,
so good morning or good evening to everybody. Let me share the screen, just a moment.
Yes, Tiziano, perfect.
You see the screen with
Yes.
slides?
Yes.
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 Okay, so I have 5 minutes, so I have to be quite fast. My part is about basic research on verification and synthesis for both discrete and hybrid systems. The first piece of research that I'm going to introduce is some progress on a long-standing problem, which is synthesizing a piece of hardware or software, something which composed with a given already existing implementation matches a specification.
Pardon me, Tiziano, if you like to show pictures and slides, we are not seeing them, but...
You don't see the picture?
No, we are seeing the your file system. It seems to be the file system, or...
Sorry, let me see. Just a second. Because I was sharing the screen, and apparently no, I have many things open.
Okay.
Okay.
You can avoid eventually the slides, and you can speak on top of them.
Sorry, because I have a lot of things open, and now I am lost somewhere.
Okay.
Let me.
Tiziano, you can.
I think when you select, maybe you can select that particular window, or you can select your entire desktop.
Yeah. I selected the Windows, but apparently, sorry, I didn't select the right Windows. So. Okay, share screen.
If you like, we can jump to the following speaker, and then we go back to you when you are ready.
Yeah, that would be a good idea. Hello, everyone.
Hello, Alberto.
Hello, Alberto. Hi.
Okay, let me move to modeling, optimization, and control. Okay, and then we'll go back to Tiziano. Okay, so the second speaker.
I'm here.
Okay, go, perfect. So
I share the screen.
Share the screen, okay, and make your presentation. Remember, 5 minutes, perfect.
Okay, so good afternoon to everyone, and welcome in particular to the advisors. I am Nicola Sansonetto, and I will outline the research developed in modeling, optimization, and control in complex systems and robotics, developed by the mathematical members that are involved in this project, underline the interaction and synergies with the other groups involved in the project. Okay, then time permitting, I will also tell something more about my research within the project in collaboration with the robotic group. Okay, the research in modeling, optimization, and control has been divided in 3 main parts that are heavily interconnected. From one point of view, there is this control of robots and unmanned vehicles, also under uncertainties. Then there is the part on high performance computing for simulation of interacting multi-agent systems, and the modeling and control of interacting multi-agent systems, which is this last part. Let me now start recovering the result in the last 2 points, and in particular in high performance computing and in multi-agent systems. Okay, it is well known that multi-agent systems have several applications in complex systems. In particular, modeling and simulation of interacting multi-agent systems have been studied at multi-scale level and from the point of view of optimal control. The line of research is divided in different approaches depending on the expertise of the members. Professor Marigonda research at a theoretical approach investigating the existence of optimal trajectories and the necessary condition for their optimality. Professor Albi research is instead dedicated to modelization and numerical aspect of multi-agent system and related optimization problem. Moreover, the numerical methods of global optimization he has been studying, such as particle swarm optimization, have been tested in machine learning with application to facial recognition, mainly in cooperation with Professor Cristani and Vip's group. The work of Luca Di Persio on this topic.
Nicola, I think your
Yes?
slide, you are probably not on the right slide, or you should start on the presentation.
It is this slide now.
Presentation results, okay.
Yeah, sure. Sorry, I forgot to switch to that. The work of Luca Di Persio instead is mainly devoted to the introduction of stochastic aspects and to mean field approach to multi-agent system. And now I come back to the first one. While Professor Di Persio is also deeply involved in the research in collaboration with myself and Professor Muradore to the topic of control of unmanned vehicles and robots. My research is mainly devoted to the control problem of robots and unmanned vehicles, also under uncertainties and interaction with the external environment. I mainly collaborate with Professor Muradore and co-workers and with Professor Fiorini and his group. With Professor Muradore, we investigated the trajectory generation problem, filtering, tracking, and control for planar robots, and also under the action of non-autonomic constraints, and possibly also under their interaction with the potential fluid or with friction. However, these tools can also be applied to different scenarios, such as teleoperation. The collaboration with Professor Fiorini and his group is devoted to the research and extended result on the so-called dynamic movement primitive methods. In particular, this is a theoretical studying that tend to exploit their invariance with respect to rotor dilation, then we have been also able to introduce theoretical basic functions that better adapt to their use in robotics. And finally, we have been able to extend the DMP method when learning from multiple trajectories required. The application of the results and also the result I mentioned before will be later mentioned by Professor Muradore and Professor Ferrini in their expositions. And I conclude my short presentation by saying that this strong interaction producing not only many research papers, that you can see here, and useful results in application, but have also given rise to many master and PhD projects, thus reinforcing the collaboration within the different expertise of the department. Thank you.
Okay, thank you, Nicola. Other questions for this part of the presentation related to the mathematical basis?
So I have a quick question. So especially given the, I mean, I can completely understand that, you know, your work has been primarily theoretical, and that is perfectly fine. But given that we just saw this impressive demonstration and the fact that you have this very nice setup, which is not very common for many other institutions to have, are you putting in some effort to utilize that experimental setup that you have, like in terms of modeling some of the machines or robots that are already there, or synthesizing something that could at least eventually at some point in time be implemented in that setup?
Okay, so far the modelization is, I will say, local. I mean, we can model and give, for example, control or trajectory generation for small part. For example, if you have to look at the arms, we are able to do this. We are something that we can do. There is a work.
When you say you can do, have you tried it on one of the robots that is already there in that setup?
Okay, not indeed in the robots that are in the laboratory right now, but in robots that are equal to them here in the lab, in the
Understood.
Implemented. Yeah.
Understood.
But there are also other research that I just mentioned that are related to the 3D printer model and to the legalization, but it's something that has just been started. From a more, say, global point of view, I must say that we don't have a model of this because it is a really complex system, which do something different from many aspects. So at the first point is that just to put together two arms is complex enough from the collaborative point of view, from the theoretical aspect of the
Absolutely. Understood. Thank you.
You're welcome.
One question I have is that are there any uncertainties that you cannot model because of complexity?
Okay. From my point of view, so I can be quite specific, let's say, we use uncertainties just to, since there is something that you cannot model, we use uncertainties to cover our knowledge in that. So, for example, when we want to model some movement, or we have many robots, we want to collaborate, or if you want to model some inertia in robots that move, or friction that we cannot model known a priori, we use this uncertainty approach. So we introduce some stochastic variables, and we treat them from this point of view. So uncertainties, we are using them from this point of view.
So is your group also considering or already
for example,
doing research in terms of the learning approach or the kind of thing?
No, so far we are trying to avoid learning approaches apart from the techniques of
I
DMP.
see. Okay. good enough,
Just,
I think.
we want to try to have a model and then to apply learning once we have a model. So to combine a classical control theory to learning approaches.
Okay, good enough, I think. Yeah, okay.
Okay, very good. Thank you very much for this first presentation. So let me go
Sorry,
back to...
I have to leave
Yep.
for my keynote, so I'll be back in an hour.
Okay, okay, no problem. We continue and we are recording the presentation.
Thank you. Ciao.
Okay. Ciao, ciao.
Ciao, Alberto.
Okay.
Ciao.
Tiziano, can you restart? Or
Yeah, sorry, just I mean, I have on my screen the oh, okay, this one.
yes. Okay, Tiziano.
Good.
Go on.
Okay,
Go on.
so let me recap. I want to present a couple of research topics having to do with synthesis and verification. About synthesis, we have done progress actually together with Alberto Inigo Inzer, who is a student, candidate PhD student in Berkeley, and Leonardo Mangiaruca from Raytheon Labs in Rome, about an outstanding open problem, which is the most general algebraic characterization of a closed form solution of the problem of synthesizing an unknown component which combined with a known part of a system matches a given specification. This is a problem that arises in many contexts. In my personal research history came from logic synthesis, which means rectification or engineering change order, meaning what you have already a piece of logic, you want to fix a bug, or you want to modify slightly its implementation without touching the already existing implementation. Therefore, you want to compose, to put together with existing logic, some other logic which together will implement the new specification or the correct specification versus the buggy one. The issue was how to find a general solution and how to characterize the specific properties that the composition operators and the components must satisfy in order to allow this solution. Our basically contribution this year, and I repeat, Alberto was part of it, was to characterize algebraically the solution with preordered heaps. Preordered heaps are a structure made by a set with a preorder and two composition operation. One is binary, a sort of classic composition, and one is a kind of involution complementation. And then we were able to define some regularity conditions, which are basically interoperability conditions, such that the most general solution can be written as X is the involution of a composition of the involution of the let's say spec with the already known part. To give a sense of what is the impact of this solution, I would say the following. Until 3 years ago, the formula for the quotient of assumed guarantee contracts was an open problem. And 3 years ago, Alberto Inigo Inzer provided a formula which was quite a big step for the community of assumed guarantee contracts. Well, now this formula can be seen as a special case and can be derived with a few lines from the new characterization that we provided. We were able to show that other formulas for the quotients coming from different domains like Boolean lattices, interface automata, languages under synchronous and asynchronous composition could be all retrieved as instantiation of our general formula. So the bottom line is, if you have a theory with preorders and your problem is to solve the equation AX less or equal than B, check whether your theory is a pre-ordered heap, and you have immediately a solution. Now I will go to a second contribution of our year of research, which is in analyzing garbage systems. We have a tool called Ariadne, which is one of the most one of the best tools in this category, meaning verification, formal verification of nonlinear hybrid systems. The developer of Ariadne, the main architect, is Luca Geretti, an assistant professor here in Verona, who is also responsible for the competition of hybrid tools for nonlinear systems in ARCH, which is the main competition in this area. The two contributions that we added this year is addressing the scalability limitation, which is a curse for nonlinear hybrid systems, by decoupling the system, followed by compositional reasoning, and then runtime verification, which is actually an ongoing work. About the first part, which is more developed, and actually there's now a version of Ariadne that implements it, we developed a theory and we presented a paper at the HCC, the last edition of HCC, where we have a theory of compositionality and computability, which tells you when you can rigorously decompose a system, preserving properties. In this way, we are able to break down a system when it in pieces which are not strongly connected. And then with contract-based assumed guarantee reasoning, we will be able to discuss the verification of the whole system by discussing on the single components. In order
devo chiederti, I have to ask you to go to the conclusions.
Yes, the conclusion is that in terms of technology, this is the contribution. We have a new version of Ariadne, which implements compositionality with on-fly composition. It implements differential inclusions, which are the tools in which we handle error analysis. And currently, we are instead working on the part which I didn't really explain, which is runtime verification. And here I have a list of publications that came out from these research lines.
Very good. Question time?
I mean, I have a similar question. So I find this work, of course, to be very interesting, but especially given that you are looking at synthesis, and this synthesis is also a very important issue in the setup that we saw. Then is there any plan also to apply this kind of synthesis techniques in that ICE lab setup, especially because also what Franco said is that currently the robots can implement some primitives, and the way then to go forward, or what is already being done, is that the robots are then composing these primitives to build something. So, at least from what you said, it seems that some of your techniques might be very applicable, especially to that setup. So are you thinking about that?
Yes, I'm thinking, honestly, we have not already done it. Let me specify the verification side. I know you asked about synthesis as applications that we do with a group of Professor Fiorini and Professor Muradore. In terms of synthesis, instead, I didn't touch a part of our research in which we work on Petri nets and temporal networks, which are more directly conducive to applications. So our plan is to apply our research on Petri nets and Petri net decomposition. We decompose Petri nets in smaller Petri nets, and we synthesize controllable temporal planes in the area of temporal networks. So we plan to work on it in the next time. But in this period, we set up the theoretical tools.
Understood. Thank you.
Okay, very good. So if there are no other questions about, we can move to the following topic, cyber physical system security. So if I'm not wrong, Mero.
I stop sharing.
Yes, stop sharing, please. And let me move to Massimo. Massimo is.
Yes.
Okay.
Hello to everybody. So let me share. My name is Massimo Merro, and I did just a screenshot of the slides just for moving a bit better. So, well, first of all, well, the point is about security in Industry 4.0 is definitely not talking on the issue. So what we decide is to divide the security aspect in at least in two main streams: cyber physical system security, well, the field where I actually work with my group, and software security, where there are a bunch of people in this department working on this, and then you will have this in a talk later on. Actually, what really is the topic of this is how you can use formal methods for investigating cyber physical system security, in order to understand exactly what cyber physical systems attacks are. Basically, breached in the cyberspace that allow the attacker to have some impact on physical process. I mean, physical input on that. In order to understand also what is now the attack surface, which is much wider, or what is usually in IT systems, and in so on in such a matter to develop statistical and dynamic techniques in order to do security analysis. Basically, something similar happened, many years ago on concurrent and distributed systems, and a bunch of tools were developed. And of course, now people that had developed those kind of tools for the distributed system now are moving to cyber physical systems. And I remember a very nice presentation by Kim Larsen, it was almost perhaps 10 years ago, was saying, well, now we need well-founded theory, model, and formally analyze cyber physical systems. Kim Larsen, just is the guy that developed Opal, which has been used in several contests for system that can be represented as cyber systems. And of course, from that point, now there are new tools. Tiziano is on charge of Ariane. There are other tools like Faber. Also, Opal is doing some variant of for dealing with cyber physical systems. So, what is our contribution? The contribution of our group? Well, basically there are two main streams. One is in order to provide formal language to understand, to specify cyber physical systems and to specify cyber physical attacks. And the point is, when you have a formal language, you can understand the behavior. And of course, usually, in this kind of system, we're talking about complex systems, so there will be probabilistic behaviors, and also you may have behavior that are not precise, but they are up to a certain accuracy. So then we are talking about matrix, and also a formal threat model for understanding what kind of attacks we are talking about, and also proof methods. That you can say, well, my system is safe with respect to this class of attacks. So also we basically have two works on this. We appeared on two journals, Information and Computation and the SCM transaction on security and privacy. Basically, one is more focused on the language for cyber physical systems and the semantics, probabilistic metric semantics, and the other is more focused on cyber physical attacks, on threat model, and formalization of the impact of those kind of attacks. I put this label in blue, so it will be easy to figure out at the end. Actually, we try to use some up-to-date statistical model checking tool on some realistic tank quadruple tank scenario in order to understand with the tool at the moment, the statistical model checking tool, where they can reach what size of system they can really deal with. Then we said there are two main threads. This was more from the static analysis point of view that we know is has fairly a number of limitations. Then we moved to dynamic analysis, actually more than monitoring, a step forward, more on runtime enforcement. Well, runtime enforcement, we investigated what might be. Runtime enforcement is a quite well-known and developed technique in formal methods for enforcing the correct behavior of certain systems. So the idea was, well, let's try to understand if this can be useful in industrial control systems where you have a bunch of PLCs, they are connected on a network, and possibly they are exposed to different threats, because as we know, PLC now, they're connected, they may have an internet connection, therefore sure they have a USB port, and there are several ways, PLC is the privileged target of malware in this kind of systems, because once the PLC is corrupted, there are, it can, the information to the supervisor of control system can be completely wrong. Also, wrong command can be sent to the physical device. Also, the other PLC might be affected because, PLC, of course, they are connected to each other. So the idea was to use to develop an ad hoc runtime enforcement technique. This was thought, basically the idea is not to force the old behavior, but to enforce specific safety properties. So, you want, your PLC.
Massimo, it's time to go to the conclusion.
Sure. And this was basically another line of research. Basically, so this allows you to have a number of guarantees. And what is more interesting is about mitigation. So, this monitor can also mitigate, do something against the attacker. So the contribution, basically, they are, as I told you, there are two threads. In blue, you see more the language part. Okay, this is actually ACM transaction. This is on the physical attacks, and this is more on the language. This is a paper that was on the statistical model checking. And the other on runtime enforcement, we published on the IEEE Computer Security Foundation Symposium, and also there is one part that was in the Italian Conference of Theory of Computer Science. Franco, have I been quick enough?
Yep, thank you. So let's we ask for questions.
Yeah, maybe I could jump in. So yeah, I find this very interesting work. So if I understood correctly, you kind of partitioned your presentation into these two parts, right? The first part was more on the static analysis, where you are doing languages and specification, and the second part was on the dynamic analysis. I already had this question, but then when I also saw the publications, this became even more pronounced, that for the first part, you were talking about CPS in general, right? And also you had the publication on water tank. So that kind of work is, when we say CPS security, it might also mean CPS infrastructure security. And then on the second part, you talked about fault injection in PLCs and so on. So there it was more focused on the industry production sort of security.
Yeah, basically the kind of attacks where we deal with, attacks they can manipulate sensors and actuators. Sensor, integrity on sensors, and integrity or drop of commands on actuators. So this is basically, actually they are called these, more technically, they are called the physical-based attacks. But then, of course, in order to arrive there, you may need some work on cyber work in order to arrive to reach a PLC to do that job. But basically, they are attacks dealing with manipulation on sensors and actuators.
So you are saying that that work is also applicable to a industrial production setting, because there are
sure. It's not a matter of software or matter of it's a matter of putting hands in sensor and actuators and having a physical impact on the process.
Understood. The other quick question I had is, because for the first part you are looking at languages and specifications, there is also some interesting work on attack synthesis. So given that you have a specification, are you also looking into this issue of attack synthesis?
Yeah, actually, of course, I couldn't explain you, but because it was too quick. But we told you this actually in this part of the runtime enforcement. This is a proxy, which is the enforcer enforcing some correct properties. This is synthesized from the properties. Okay. And so you give some property, say something like, when the level is below a certain point, the pump should be on. Okay, this is a safety property, and you synthesize from this property, you synthesize a monitor that enforces this. So it takes the output of the PLC and eventually change it or drop it, because in order to maintain the properties. So we're doing synthesis in this sense.
But there could be synthesis in terms of runtime monitoring, right? Like, for example, you say that if this happens, then that valve should be on, or if this happens, then the pressure should be more than this. But what I was thinking of is that any action that violates that is essentially potentially an attack, right? So can you also do not just synthesis of the runtime monitor, but also synthesis of an attack which would essentially be like anything that violates what is the good behavior that you are interested in?
Not really synthesis. We have a language to express those language, to express attacks, but not synthesis. Not synthesis in order to say, I want that goal, let's synthesize an attack that reach that goal, if I understood correctly.
Exactly.
No, we are not yet at that point, but this, of course, would be really nice. Something like, I want to reach that goal. Let me synthesize an attacker that to reach that goal under certain conditions. That, of course, there should be some kind of stealthiness conditions in order to reach that goal. You have a good chance that you reach that goal.
Right. So what I was thinking of is that, because again, as I saw in the first part of the presentation, that industrial demo, there are things like assembling Lego blocks and so on, right? So I feel that in a setup like that, one could probably really synthesize some attacks automatically, right? That this is what I want to assemble, this is what the robots would do, this is my final goal. So what is a possible physical disruption to that? That goal, right? And that could be like an attack.
That's a very good point, a good intuition. I've not investigated that, but it's really nice to investigate for sure, definitely.
Okay, yeah, thank you very much.
Okay, very good. So we just finished the first part of the presentation related to synthesis and verification. Now we can move to the following part related to data and process modeling. And the first one is the fusion of IoT and industrial IoT. And let me ask Florence Demrosi take the control. Florence, export your presentation. Okay.
Okay. Hello to everyone. Do you hear me? Perfect.
Yes,
okay, I will start my presentation. Let me know when you see.
Yes, we can. Go on.
Perfect. Thank you very much. So this presentation will be about the fusion between IoT and IIoT. So everyone, I think, knows that when we talk about IoT in general, we think about wearable devices that we normally use in our daily life. Instead, when we talk about industrial IoT, we enter in the field of heavy machineries, smart cities, automation, factories, and production lines, and also in some cases about healthcare. The purpose of the consumer Internet of Things is that of improving consumers' quality of life. Instead, when we talk about IIoT, the goal is that of improving the production process. In the IoT, the normal IoT, the interoperability is not the main issue because the objects, the devices that we normally have, most of them can work independently without the need to communicate with each other. But when we talk about industrial IoT, we have to face issues related to the integration with the existing systems, because we know that the existing systems, the old-fashioned devices that are integrated in the manufacturing plant need to be maintained and integrated with the new devices. From the point of view of false management in the IoT, this is an important issue. However, in the IIoT, this is a critical issue. But let's see an example of an IIoT architecture, the simplest example that we can have. So for example, we have a working environment with a worker in this case, and we have machineries that are controlled by the worker or that are autonomous in their process. And this creates our device layer. These machineries and these working environments provides us the data that helps us to recognize and monitor the environment and also the devices. So this device layer generates the data that are transmitted through a network layer to a service layer. On the service layer, we can compute over this data, monitor it, control, reconfigure the device layer or the process that we are generating in the device layer, and also can give the control to a content layer over where we have the user that is controlling, observing, and reconfiguring the production line. However, we know also that one of the main problems that we face in this context is the absence of a unique standard for the communication of the existing devices in the device layer. In particular, we have different kinds of sensors or actuators which communicate with different communication technologies and communication protocols. And many times these protocols are also proprietary protocols. And at the moment, the best solution are gateways. So we need gateways which support all these different communication protocols, and these gateways provides also additional level of security. And in the field of edge and fog computing, these gateways work as edge devices or fog devices for pre-processing of the data. This pre-processing then reduces the size of the data that needs to be transmitted and to be handled by the service layer. But in this scenario, okay, our goal, the goal that me and Graziano have been working on, is that of monitoring the working environment and the equipment status. With regard to working environment, we want to use the existing architecture that we show, the normal architecture, the basic architecture, to monitor the workers inside the environment or the people inside the environment. Instead, with regard to the equipment status, we want to monitor the equipment, so the sensors and actuators of the device layer. So to make a simple example also related to the IceLab, as we showed during the demo, we have inside IceLab different sensors, mainly related to environmental sensors, so temperature, brightness, smoke, presence sensors, and also humidity sensors. In this right part over here, these sensors are integrated with the plant itself, so with particular devices of the machineries of the plant. Instead, on the left part, we have environmental sensors. Besides using these sensors in this IoT sensors research context, that are actually real sensors, we are using also additional sensors that in this case are the Wi-Fi, let me call them sensors, are the Wi-Fi sensors, or better, they are the Wi-Fi routers or BLA devices, because we are using the radio signal that these devices emit in order to recognize the configuration of the environment. Just think, for example, that we are able to recognize if the plant is turned on or is turned off based on how the propagation pattern of the radio signals changes in time. Okay, so on this idea, we have been working and we have created a system that works both for home environments, but also inside the IceLab, that based on the analysis of the BLA signals, so radio signals, Bluetooth radio signals, and Wi-Fi radio signals, is able to recognize how many people are inside the environment, and in this case, basically also if the environment, if someone is inside the environment or not, and also estimate the distance between the people inside the environment. So we make use in this case of channel state information from Wi-Fi signals and of RSSI values or receiver signal strength indication from the Bluetooth radio signals. This system is not invasive, it's device free. So it means that users inside the environment are not carrying any type of device that interacts with our system. So we just need in this case a Raspberry Pi, for example, or just a smartphone in a fixed position that is able to recognize the status of the environment. And this is the first goal and the first research context in which we have been working in the ICE lab. The second research context regards more the standard sensors, the environmental sensors that we show before. And the aim of this second research context is that of creating an architecture that in our case is based on the FEWARE framework to add and remove sensors and actuators from different producers. So these sensors use technologies, communication technologies and communication protocols different between each other, and the FEWARE architecture provides us the capability to integrate these sensors and actuators in the easiest way. So we created the first layer of an interface for the user to easily add new sensors and actuators, and in the next steps we are aiming to automatically synthesize services from high-level user requirements. In this case, the idea is that a user provides a high-level requirement, then we formalize this requirement based on the previous history of the environment. We are able to understand which are the sensors and actuators that can act on these requirements, that can make become true these requirements, and then we need to synthesize a task that will be deployed over the environment. So, and at the moment we have published the paper at date 2021, and now we have also other two papers under review process in IEEE Sensors Journal and IEEE Internet of Things Journal. So I think that was quite fast. Thank you very much.
Yes. Thank you very much, Florence. So I'm sure there will be questions about your presentation.
So can you say a little bit more about the synthesis? I understand that you are trying to do automatic reconfiguration, but when you say that you are, what kind of reconfiguration are you doing, or what kind of synthesis are you doing here?
So in this case, actually, I'm not working at the synthesis part. I am more working on the, because the synthesis part, I think that is the one that already has a lot of work in the literature, many tools that can provide synthesis, let's say, or just can create this, the synthesized task. We are working more on the selection of the smart devices. In this case, we are starting from the database of the data collected from the environment. We are using causal discovery over time series in order to find the relation between actuators, sensors, presence of people inside the environment, in order to find also some dependability. So for example, at a certain point, if we turn on the AC, okay, after 10 minutes, we will have an increase of the temperature of 5 degrees, for example, or a decrease in this case. So I am working more on this part. So we need, first of all, to recognize.
But what exactly is the goal? That is what I'm not understanding. So okay. As I understand that if you switch on the AC, then the temperature should fall by 3 degrees within 10 minutes, right? This is like a specification, or this is the expectation. So is it that you are now monitoring whether that expectation or specification is being satisfied or not? Or what is the goal of
no, the goal is, let me explain it by a simple example. For example, I am going out my home or out of the laboratory, and I I tell to my smartphone or to the interface that I need that the temperature has to be stable at 25 degrees. So first of all, we need a system that tells us how to maintain the temperature over 25 degrees and which are the actuators, okay, that we have to turn on or off or over which we have to work in order to achieve such goal. So to do this, we are studying the behavior of the past behavior of the environment in order to find out what is the relation between the actuators and the temperature in this case. So for example, what happens when we turn off the an actuator with regard to the temperature? Once that we are able to find these relations, then we can say, I need temperature at 25 degrees, then which are the actuators that I have to work on? And in that case...
But I'm sorry for interrupting, but this example, I unfortunately don't find to be very convincing, right? Because let's say I want to reduce the temperature. I know that in order to reduce the temperature, I will have to switch on these and these air conditioners. This is already known. So the fact that, I think I understand what you are saying, the fact that you are trying to discover that in order to have this, what are the things I need to do? But what I'm missing is what is the need for this kind of a discovery, and the temperature example probably is not a very good one. Is there some convincing need for discovering something like this?
In this case, yes, the main part over here is to discover that relation that you said. So we don't start with the knowledge of who is working on the temperature. We need to discover who is working on the temperature.
But maybe something like a fault might be a good example, right? Okay. So let's say in an industrial setting, I would like to find out what is happening because of which maybe there is more wear and tear in a drill bit, right? Or what is happening that is leading to a certain machine failing regularly. I think if you could discover things like that, I think that would be probably a more convincing example than saying, what is it that I have to do to reduce the temperature, right? That is something that is already relatively well known. The other question I have is for the first part, I also find it very interesting that I think what you are doing is this, looking at this Wi-Fi interference to deduce how many people are there in the room and so on. I can also see that there could be interesting implications of that in terms of security, right? Because just by looking at the Wi-Fi signals, I might be able to conclude a lot of things, and this might be a potential security threat as well. Yes. So given that there is another group in the project looking into security, are you also thinking of some collaboration with that group?
Yes, for sure. We have been thinking, and I have read also on the literature that have been some research groups also outside from University of Verona, and from which we can start from what they have already done, which propose some modification in the communication protocol that will avoid these security issues. So someone is trying to, let's say, encrypt, okay, the child state information from the point of view in order to not provide to external observers the capability to recognize what is happening in our environment. And this can be for sure a good start for a collaboration here in Verona.
Right. So is this the work that you are doing with Philip Kind?
Yes. Yes.
Okay, understood. Okay, very good. Thank you.
Thank you.
Okay. Very good, Florence. Thank you very much. So we can move to the next presentation. The next one is about the architecture for data collection. Damiano Carlo. Wow, perfect, Damiano.
Okay. So, I don't know if you can see the slides.
We can see the side of the slides where you have the control and not the other one.
This one?
Okay, now? Perfect. This one is
okay. Okay, so This is the work we have done with Lisa Quintarelli and Berto Berussi and Sara Migliorini on data collection architecture. And as presented before, we have a set of sensors. And the presentation before was about the sensor for the environment, so temperature, humidity, presence, and so on. But also the equipment, the different equipments also expose their sensors and their data. And so we have to collect such data, and they are exposing them through a server. So the main task of this activity was to create such an architecture that should be scalable and can be changed according to the requirements. And so this is the main architecture that we developed and we deployed also. And so we have a set of clients that collects the data from the different equipments and from the IoT sensors. And then all this data has to be collected by a data buffer, which is a pub/sub system that can scale depending on how much data we are collecting. So even if in the future we are adding new sensor or new equipments, we can keep up with the data produced by these equipments, adding more data buffer. So we have a data buffer, so we can split the data production and the consumption. So the data then is divided into different topics, and so there are different actors that consume the data and put the data in a time series database. Why we choose a time series database? Because of course all the data is has timestamps, and so is characterized by a time series, so it's useful to have it stored as a time series. Then we can take the data and do some analysis on this data, and we can also upload the data in some commercial or private cloud, such as MindSphere, which is offered by Siemens. And of course, Siemens also with MindSphere offers a lot of tools to analyze the data, but it's a commercial product, and we wanted instead to do all the things in-house, so we can process and try to extract information directly on the premises, so on the plant. So this is the high-level view, and actually, yeah, the main work, I'm not going through the different pieces, but just the final results. And so the main activities was to evaluate the different solutions for this architecture. And so the time series database, the pub/sub system, and once we have identified the different solution, we have also deployed them and integrated the different parts together, and also with the system already present. And also we have developed a set of tools that can simplify the data ingestion and processing. So if we add different sources, we can then add them to the system easily. And also and this was mostly implementation. Then we have also the research part that is then dedicated to how we can manage the data itself, so we can divide the data, so we can partition the data in the system, in the NoSQL system, and then once we have the data, how we can extract information, so we can analyze the data, the time series that we have memorized, so stored. So the results are in this publication that you can find also in the report of each of us. And this concludes.
Thanks, Damiano. Question about...
I mean, one obvious question that comes to my mind is one of the main goals of Industry 4.0 is also things like proactive maintenance. And because you are collecting all the data, what are you also doing in terms of future prediction and issues related to things like proactive maintenance? Or are you also collaborating with other groups
Yeah, sure. This is a very interesting question. In order to do it, we need the data itself. So our group at this stage was focused on creating the infrastructure to collect the data. Now that finally we have this infrastructure, we can work with other groups in order to extract information, and one of these useful information is predictive maintenance, of course, because we are also creating different ways of collecting data at the scale of under millisecond. So each movement of the robots and everything, we are recording everything. So from these data, then since it's related to the equipments, then we can do all the different analysis.
So in addition to proactive maintenance, I feel because today so many things are done in a data-driven fashion, you could probably also do things like identify bottlenecks in the production process, maybe identify alternative synthesis approaches which are more efficient, maybe use this to also check whether there is any security vulnerability and so on, right? So I kind of feel that given that you are dealing with this efficient data collection and storage, you could link to many of the other groups working on different things and see how they could also be able to use or utilize the data that you are collecting to improve many of their processes. So
yeah, sure. And of course, we need also the input from them. So what they need. And we are also preparing another thing that I didn't mention. We are also preparing the visualization point of view. So we are preparing different different views that depending on the people looking at the data, they can check what is more interesting for them, and so this is one of the tasks that we plan to do next year.
Very, very, very interesting. Thank you.
Thank you.
Very good, very good. Okay, now before going on the digital twin, we analyze a bit the problem of network synthesis. So let me ask Davide Quaglia to start. Okay, Davide, your turn. Okay.
Okay. Thank you. Good morning and good afternoon. And this part is related to the so-called network synthesis. So that this part is focusing on communications in the factory, in the industrial context. Communications are now becoming more and more important, but also the infrastructure is becoming more and more heterogeneous, larger and larger, and furthermore, the co-design, we argue that the co-design of factory plant and network is a key factor to unlock unlock optimization, to do a better design. I will show just 4 different aspects of network synthesis, different case studies which we are addressing in the project. The first one is the design of the network infrastructure itself, starting from data flows from the different part of the shop floor. We try to optimally map such communication on different network architectures according to constraints, for example, delay, bandwidth needs, and also optimization goals, for example, economical cost, reliability, and so on. The second case study is a little bit at a higher level in the network stack, is related to the fact that, as seen in the previous presentations, there are a lot of monitoring flows in the factory, in the plant. And one question is how to position in the optimal way the equipments which are dedicated to the transport of such information. In particular, OPC UA was already mentioned as a new standard, an emerging standard for the delivery of such information. So how to which is the optimal position, optimal placement of OPC UA servers inside the network infrastructure. The third case study is related to network security. Again, in the factory, there are a lot of flows, of communication flows related to, of course, normal operations, but also interaction with the cloud, as discussed by Damiano, but also in specific cases there is, for example, maintenance. You have communication for local maintenance or remote access for maintenance. So starting again from this set of data flows, which is the most secure segregation of the network to protect, for example, during maintenance, how to better protect local communication from the presence of other kind of sporadic communication, for example, for maintenance. And the last case study is related to a particular application we are developing currently in the project, which is an optical tracking system to track workers inside the plant for safety reasons. And this kind of application, of course, involves several aspects. First of all, in computational vision, machine learning, of course, but I am addressing the problem from the communication point of view, using network synthesis to explore different way to move information for optical tracking, for example, by using edge computing or fog computing or cloud computing. That is the best place to put machine learning inside the infrastructure. This slide just summarizes the previous discussed achievements. The last one was not discussed and is another activity which led to the development of a simulation platform for the simulation of the behavior of OPC UA communications inside the plant. Regarding research results, there is one publication in the just finished date edition, and furthermore, a new project has been founded. It's just a news from the last at the end of last year, was funded by Fondazione Cariverona for 100 kilo euros. And the topic of the project is privacy preserving monitoring of industrial activities to enforce health safety of workers, of course. And this is interesting because this is a project which merges several activities of this project, which are discussed just today. And all these activities are merged in a specific topic devoted to health safety in the industrial environment. And that's all from my side. Thank you.
Okay, thanks, Davide.
Yeah, hi, Davide.
Hi.
So one question I have is, because you are looking at network infrastructure and also you said positioning of the monitoring equipment, I find that to be a very interesting idea. Now, are you only looking at static design, or are you also looking at dynamically changing the network monitoring infrastructure because or the network infrastructure? Because I could imagine that in a production system, the production process is going through multiple phases. So in some phase, maybe one network infrastructure is optimal, but in a different phase, a different infrastructure is optimal. So naively speaking, I could also think of, wireless routers or other such equipment being positioned with robots, and the robots are moving around. And as a result, the network infrastructure is also dynamically changing. And also for flexible manufacturing systems, you are not doing the same thing at all times, right? So can you look into dynamically adjusting the network infrastructure, which I think would be a very interesting problem on its own?
Yes, sure. So in fact, the idea is to try to reduce the computational complexity of the synthesis process, which is basically an optimization process, to make it feasible at runtime, so during operation. So it's possible to, currently we address the problem of plant reconfiguration, not a very dynamic scenario in which, for example, a mobile robot is moving. But for sure, for dynamic reconfiguration, we can address the re-execution of the optimization to adapt the network according to the new configuration. Yes. Thank you.
Thank you. Thank you.
Very good.
You're welcome.
So, okay, so let me move to the next topic. The next topic is the presentation of myself about digital twin. So we are still exploring all the modeling of the processes and the data. And we know what is a digital twin. That is, a digital twin is digital replica. And we can subdivide possible digital twins in 3 different categories. Autonomous, in the case we have models for each component of the digital twin, connected, and when it is connected to real sources of data, the names usually digital shadow, and hybrid, when we mix the reality and what is simulated based on models. We approached all the different digital twins in HICE, and the most important research results about has been the identification of the methodology for the design, the automatic, more or less, but mainly automatic design of a digital twin, starting from sources of information. We explored, first of all, the idea of summing, adding all possible information into an automation ML description. Then realized that automation ML is not expressive enough to represent all the characteristics which are fundamental to automatically generate a digital twin or other models of the system. And then we just migrated to SysML. We found some version of SysML oriented to production cyber-physical system. And we are collecting into this kind of SysML information coming from example for the manufacturing execution system, or from BPMN models of the operation, or from different taxonomy and so on. As soon as we collected all information together, then we are able to synthesize some description. And for example, to collect information, we can start by using BPMN representation of the processes, of the actors, of the machines that we have, the machineries, or by starting from ISA 95, we can connect information coming from the manufacturing execution system, or by using INL also has the sources of information, we can obtain some other information about the layout of the plant and some other stuff. Putting all together, we need to give a formal representation of all such information, and we use a SIM guarantee contract to add the formal description and to check if all the composition of all the previously described parts is correct, and then if we can start to automatically generate something. An example is the automatic generation of the digital shadow that you saw during the demo, and this has been automatically generated from the point of view of the skeleton, with the point of view of the OPC UA clients and the servers, and with the point of view of the interconnect between all of them, to obtain an execution of the system which monitor the actual execution of it. And this has been important, and in fact, we reached some implementation results with respect to the HICE lab. we have a digital shadow. We also have a digital twin in which we are mixing the shadow with some models of machineries which are no longer there, and we can have a simulation which interact parts of data coming from the reality with some others which are synthetic. And then we have the methodology that I've just reported to you. This also produces some research results, and particularly interesting is a transactional industrial informatics about the virtual prototyping of a production line using assumed guarantee contracts, and another paper on transactional computers. Final point, to also answer to a previous question, we can use the digital twin also by adding errors and by mixing models, error models with the simulation of the digital twin in order to obtain data for performing analysis which go in the direction of predictive maintenance or in the direction of analysis of the functionality in presence of errors. This is the area related to digital twin. I don't know if there are questions. Or...
No questions from my side. Franco, can we take like a 2-minute break? Like
yes, for sure. Yes. We can take 2-minute break and we go back 10 to 5, in 5 minutes by now. Okay? We'll start in 5 minutes by now.
Okay, thank you.
Okay, you're welcome.
We apply the same approach to a real case scenario, the one provided by this company. So we collected 3 weeks of production data from a 10 phases process with 5 minutes sampling. And we collect all 169 features describing the overall ultra-processed food manufacturing process. Then we perform with the support of the experts a pre-processing phase, and we consider only five phases and 14 significant features. We apply the same approach that we use in the synthetic case to recognize a relationship among variables. And yeah, the results are a little bit confusing because the complexity of the real case make not straightforward the applicability of the method tested in the synthetic case. So the next step is to apply or to do the data collection in the ICE production line to get a more controlling condition and to better evaluate the influence. In any case, these results has been considered useful from the companies because the main focus is on the first stage where there are most of the dependency, but usually the companies are changing parameters in the last steps of the process. So we have also developed some software tool that we plan to apply in the case in the ICE line, integrating the edge computing facilities. So these are mainly the contribution in the data acquisition that we plan to extend to the ICE lab and also in the computing methodologies. So we have got also a couple of publications. We are also working to another one that try to use the temporal dependency to better model and as a prediction model for the process. So that's all for me.
Thank you, Diego. Yeah. There are questions for sure, I presume.
I have a question.
Yeah.
So if I correctly understood, the purpose is to increase like the production process, right? Ultimately.
Yeah, it's to better understand, to try to get a better understanding of which are the most important variables. Because when, let's say in particular, if you consider Industry 4.0 case where you are changing most often the production because you have smaller branches of products. So you are going to change the production process more often than in the past. And so it can be useful to better understand which are the most important and how the variables are interacting. We are just focusing on temporal relationship in this study. So this could...
But after you have identified the dominant variables and their interactions, then you would like to ultimately use that to somehow revise your process, right?
Yeah, the idea is to, now we are trying to use both the cause-effect relationship, but we are also able to reconstruct the time gap. So the variables 3 time step before is affecting the actual value of the, so we are trying to apply these constraints, so this relationship to improve prediction models to try to predict some quality variables that are important for the manufacturing process. Of course, in a real scenario, let's say we started from the real scenario because it was, let's say, due to the pandemic situation, we were not able to get the overall access to the ice production line, while the companies continue with the production. So we were able to get access to the data. So, but yeah, we plan to try to do some predictive modeling to use this information.
So the let's say the utility of this process, or how you are going to use that data or the results from this exercise, that will depend heavily on whether the production process is a fully automated production process, or does the production process involve substantial amount of human intervention. So when you said that you work with this food production company, how was their production process? Was it like it involved a lot of human interactions and humans, whereas the ice lab, what you are doing is a more automated? So I'm just wondering how you take into account these issues, and how do you extend those experiences into a more automated production process?
Okay, let's assume that since we are in ideal, and also the companies has a really modern production line where most of the process variable are recorded. So we are able to reconstruct the human intervention from the data collection, even if they are not automatically tuned. So we expected to be able to apply the same methods also in the ice lab, even if the control of the process of the line parameters is automatic. But of course, thanks to this study, the company decided to extend the number of variables that are monitored, because some of them in the original acquisition were not recorded in the standard database. So we worked with the company to extend and to be able to better model also the human intervention, because this is one of the limitations. We were not able to reconstruct any relationship, or also to model variables that are not recorded.
Understood. Thank you.
Thanks for the question.
Okay, very good. So let we go on in the direction of the abstraction. So now is the time of model extraction from manual task. Paolo Fiorini. Paolo, you can take the control. Okay, perfect.
Right. Well, good afternoon, good morning, good night, whatever is appropriate, especially to my old friend Sukan, who's I guess both Alberto and Sukan are a big customer of coffee in this time of the day. So my presentation will not be as exciting as the Mars landing, but I'll try to make it pleasant. So we are looking at the future of the use of the laboratory. If you remember, the laboratory is one of the goals is to have these fully reconfigurable recipes to make a product. But very often there is also the need of having human presence to do some assembly and disassembly. So how do we model these tasks? So we start, and this is the result so far of a parallel project on robotic surgery, where we have a teleoperated action of the surgeon over the body, and the teleoperation is a very nice medium, so to speak, because it forces the human actions to be very well codified, and by recording the joint axis, by recording the variables of the teleoperation robot, you have sort of an intermediate step between the fully manual and the automatic system. So before going into the understanding of the full manual task, we do this understanding of the teleoperated task, which is an easier step, and then we go into this into the full manual with the next phase of our project. So how do we get this knowledge? One of the key points is to transform the knowledge of an assembly task or any manual task into a recipe for a robot. So we are following two paths. One is the top-down path, so basically from recipes, from books, from interviews. This is the nominal activity. So basically, it doesn't account for the outliers of the intervention. It doesn't account for some glitches here and there, but it's the nominal execution. And then we also have the data-driven learning, which accounts for the real execution. So how do we get the knowledge from these two approaches, and how do we combine them? So this is the output that we have in this task. So for the top-down, we started some machine learning from written text, and we use the surgical books, which are actually, in terms of recipes, are very algorithmic in a sense, and we do some machine learning on that. And we have, unfortunately, to generate the ground truth, we have to generate cases, and so it's a very long and tedious process. And those cases have to be validated by our surgical colleagues. And again, these are example of generating example to do the training of the machine learning. And we did a number of tests with different models, and we obtained some useful result. And the other point is that these recipes usually do not account for all the background, so we need to generate some ontology of the surgical process to get all the information that are needed. So this is another part from related to the top-down approach. And the bottom-up approach, you heard one part in the presentation of Nicola Sansonetto on the continuous component, and then the discrete component is to be able to define this hybrid automaton that describes the sequence of teleoperated and then manual tasks. It's not an easy problem, because we need to solve both the state identification, and then within the state define this continuous model, this DMP, as was defined earlier. But with the adding the constraint of limiting the type of continuous motion that we have, we are making some good progress on that. So this is the full problem that we are trying to solve, and again is not an easy problem. And we are working with our friend at Caltech, Joel Burdick, to work on this problem together. The DMP is very interesting because it allows for motion scalability. You see here two trajectories that are learned on the left and executed on the right, and they look similar, but in effect the scale is very different. And so this is one of the extensions that we made to this DMP approach. From state to state, we have to do to define the transition, and we use a logical programming, this answer set programming, because it allows explainability. So we are not using a neural network for the whole process, but just for specific functions. And for representing the logical evolution of a task, we use this ASP programming because it allows an easier interface to the surgeon or to any human operator. And these are the examples that we have. For instance, here in this In this example, we have a training task where the grippers have to pick up rings of different color, pass it from one gripper to the other, put it on the right peg, replan when the ring drops or when there is a mistake, and it's all done autonomously by the robot, identifying the position, defining the end of the task, and so forth. And again, these are our implementation. We are modeling the expert knowledge. We are developing machine learning task, and the general representation of this manual task is hybrid automaton. And these are our research results. We have a number of publications. Some are also reasonably good, and that's about it.
Very good, Paolo. Questions?
So one question that immediately comes to my mind is that there is so much work now on things like transfer learning. So are you, looking into, or is that already incorporated? Because you said that you are already also looking at machine learning based approaches.
Yes, it depends what you mean by transfer learning. For instance, when we do the learning of this autonomous or the continuous part, we learn it on a different setup, and then we transfer it to the surgical setup or the assembly setup, and that works. We also do transfer learning when I didn't mention it, but we have another line of research on simulation. And of course, if you want to simulation of grasping flexible tissues, and of course you cannot do the machine learning with the real hardware because it breaks very simply. So we have developed a simulation environment, and we do the simulation environment with a finite elements model, so we can do the learning on a finite element models, and then transfer and use the same neural network to do the planning and the execution of this specific task. And so again, this is another example of transfer learning from one environment to the other. But again, we use this deep learning only for specific application, because we don't feel is well, the main problem is that you cannot understand what's going on if you're using the net for a long process. You really don't understand the reasons, and so we prefer to limit it to small temporal sequences or small tasks.
Understood. So the other question that I have is, let's say you have, you mentioned, which I really liked, that in many cases there could be textual descriptions of procedures, which could also be more algorithmic in nature, and you could learn that and try to have a robot implement or follow that procedure.
Exactly. In fact, if I go back here, I didn't describe it, but you see here we define the knowledge that is on the text, both in procedural and declarative knowledge. And so the procedural is all the sequence of action that you're talking about. And then the declarative knowledge perhaps is missing things, and then we need to go to the ontology.
Right. So my question is that both in this case as well as cases where, for example, there are lots of videos or demos that we can see today that you hold a human holds a robot arm and shows how to do something, and then after some time the robot kind of learns how to do it. And in this context, the question that I have is, although the robot is achieving the same goal, let's say the degrees of freedom that the robot arm has and the degrees of freedom that, let's say, a human hand has or another robot hand has, they might not all be the same. So therefore, let's say eye teaching or even the textual description might have been intended originally for a human. So making the robot do the same thing might not be the most efficient way of doing it, right? So in some sense, if I may say this, it is something like, let's say there is a robot monkey, and I want to teach the robot monkey how to climb a tree. So I try to climb the tree and tell the robot monkey do the same thing, but that might be a very inefficient way of doing it, because the robot monkey might be able to climb the tree in a much better way, or jump much higher. So the steps that the robot monkey should take to climb the tree would be very different from the steps that I can possibly take. So I am just wondering, how is that incorporated
Well, you're perfectly right. In fact, we are seeing already the same thing here well, there is no time to go into the details, but when we do this ASP, we write the program the way we would think about it and we do it, but then all the rules are optimized, and actually the execution of the robot is a much simpler and faster flow of execution. So here is only a sort of logical optimization, but the same line of reasoning applies also for the manipulation. And not only for improving, but we have to make the translation between the high dexterity of a human hand and the limited dexterity of the gripper. So there are going to be some sort of lost in translation that will happen somewhere, but we haven't addressed the problem yet. But it's clear, and we are aware of that.
Understood. Okay, thank you.
You're welcome.
Okay, I have one question.
Yes, you can.
So I think it's very interesting talk, and so what's the relationship between the procedure you expect from sentence that include procedure and also ontology? So
that's a good question. Okay, so I need to open a little parenthesis. So for the execution itself, we would not need any ontology, because we assume that when we do the planning, we have solved all the declarative knowledge, we have defined everything. However, and of course we need the ontology in that phase, but not during the execution. However, if there is an unexpected event, or we are starting next week with some experiment on partial nephrectomy with kidneys with tumors of different complexity, and we want to see how our system can react and replan this task. So in some of these replanning cases, we may need to use some knowledge that is not already embedded into the plan. And so in this case, we want to access the ontology. But again, is because, for instance, the question is why the spatial unexpected case is not included in the nominal program. Probably because it's an outlier. It is not didn't make it into the average of the nominal model. So perhaps an alternative to ontologies is to have a fast access to the database of all the experiments from which we learned. And so that is a knowledge that sort of stored away and that we can retrieve it in case of necessity.
Okay, thank you. Also, one last question. I presume that you use the DMP to implement a kind of skill, robot skill.
Yes.
But what if there is some uncertainty in the, let's say, robot position or target position, whatever? Then how the DMP could work? So I think that some people consider that one and then extend it to include some sort of some reinforcement learning that will use vision to take image and then combine this DMP or whatever. So that's what
we do the same. We do the same. We don't use reinforcement learning in this case. We use visual servoing. So basically,
I see. Okay.
We are moving according to DMP, but when also for taking in account the obstacles. If you have an obstacle that wasn't at the beginning, you need to have a sensor that then set up a force field so that it changes the DMP. And the same thing is for the goal. If the goal is changed, then we have a force field that forces the instrument to go to the right target.
Okay, thank you very much. Yeah.
It's a pleasure to see you, Sukan.
Nice to see you.
Okay, thank you very much to all. So let me move to the next level, that is we pass it through synthesis, verification, data, and process modeling, and now we arrive to the applications. And let me ask Nicola Bombieri to start with the main problem of applications about edge fog cloud computing. Nicola?
Okay, yes. Thank you, Franco. Let me share
the screen.
Here we are. Do you see
yes,
the right slide?
Yes, go on.
Okay, thank you, Franco. So here we address the topic of software design and verification for heterogeneous architectures from the edge to the cloud. And in particular, the software development for robotic platforms, so for mobile robots in particular. I think there is no need to motivate the edge computing and also the combination of edge computing with the cloud computing. So I would rather go directly to the main challenge of our work. So here we have to face the complexity of the software development for the mobile robots, considering that the software is multi-domain. So we have several tasks coming from different domains, and that these software applications have to satisfy not only functional constraints, but also non-functional constraints. So the software has to be not only correct, but also energy efficient, has to satisfy performance constraint, reliability, and so on. So what we did, I mean, the main contributions in this topic can be can be grouped in two main sets. The first is for the software design point of view, and the other is the verification point of view. Concerning the first one, we have been working on developing a methodology and implementing a tool chain to help the programmers in developing this kind of software applications. So we defined a tool chain which is based on standards like Docker for containerization, Kubernetes for orchestration, ROS for the integration, and so on. And we defined this tool chain, which consists of several refinement levels. So the programmer can start defining the software, and then through refinement steps, it can verify and refine the software towards the actual deployment into the final robots platform. The tool chain has been published at DAC last year, and the use case was the preliminary software application that we thought to use in the ICE lab for our mobile robots. Actually, at the time we developed the tool chain, the mobile robots were not available in the ICE lab. They were traveling from Spain, a journey that took around 6 months, by the way. But now we are applying the tool chain for finally for the right robots, the Kairos from Robotics. And so this was the first step. Then, considering that this kind of software has an important part of embedded system applications. So we worked on defining new mapping and scheduling algorithms in order to improve the performance of the software for heterogeneous architectures, and especially for edge computing. And the results have been published at DATE last year, or better, the first part at DATE and the second part in the Transactions of Computers. Okay, considering the second set of contributions, considering the verification side, we have 3 different contributions which are integrated. Because our main goal was to define an environment, a verification environment by which we wanted to control the behavior and the tasks of the mobile robots through runtime monitors. So we defined, this is the first contribution, a tool. We implemented a tool by which, starting from informal specification, we can synthesize the monitors, which are, checkers or pieces of code. And the goal was to integrate these pieces of code directly with the rest of the software, implementing the actual behavior of the robots. The problem is that these kind of checkers many times are very heavy and many times can compromise the real-time constraints of the other tasks. So in the second contribution, we defined a methodology and a tool that can orchestrate and can distribute these checkers across the different components of the computing architectures. So we needed to have the checkers very close to the edge and very close to the, inside the robots. But many times when there are particular situations, the goal was to move the monitor outside the robots, for instance, into a server or directly to the cloud, without losing the status of the state machines implementing the monitor. And so this was the second contribution, and the methodology and the toolchain was published at date last year. Concerning the third and final and last contribution, well, actually, when the bug was identified by any monitor, the problem was to understand whether the bug was a false positive or an actual defect or vulnerability of the software. And so in this part, we developed a tool to automatically understand, or better, to help the verification engineer to understand what kind of problem caused the bug and the monitor to be enabled. So here we have the list and the summary of the main contributions of this talk, of this topic, going from the design perspective to the verification, and the corresponding publications. And I think that that's it. If there is any question.
Well, I have a question. In general, the issue of mapping a software on an heterogeneous platform is like a nightmare, right? You pointed out it's difficult, but sometimes it's even impossible in my view. So, and developing the software without being cognizant of a platform is also a bad idea. So, whoever is developing the software should have an insight on what the platform look like. Because if I have, for example, the capability of doing certain computation on a GPU, just to make it a stupid example, then I can choose to have an algorithm that is heavily mathematically based. If I don't have a GPU, then it's a disaster, right? So I have to change my algorithm on the basis of what is available to me, and also on the basis of the timing that it takes to distribute the task, right? Because if you have a long latency to access some of the platform, then it's going to be a disaster, right? So, and one of the problems with Kubernetes or other containerization techniques is the fact that performance is not guaranteed. So I'm working with Siemens actually to try to solve it problem, to do that containerization in quote unquote real time. But it's challenging. It's really challenging because it's like to have a cake and eat it too, meaning that you want to make things independent as much as possible, but then by doing that, you give up so much performance that you need to discover some other mechanisms. So while I believe that your approach is really interesting, I think that without connecting in a deeper way hardware and software, I don't think it's going to be viable from an industrial point of view.
Yes, I think that you, in few words, underlined the main difficult parts of this work, and actually fighting toward the real-time constraints when we containerized all the tasks is a very difficult part, and we are working on in this period.
Yeah, and it's not easy. I mean, don't hold your breath. You're not.
Okay, very good. So if there are no other questions, let me move to the software security. So, Mariano.
Good morning, good afternoon, good evening, everybody. Let me share my screen.
Perfect.
You should see my desktop now and my slide now.
Okay, you can go on.
I will talk about the progress of software security, basically by starting from this slide, because software security is a quite pervasive requirement in industrial automation, because usually industrial automation is a composition of many different components and devices, and the compromisation of one single of them, one single component could compromise the overall security of all the infrastructure. So security should be addressed on a layered point of view and also in a quite pervasive manner. During this presentation, I will try to give a sketch of what we did last year about software security across these main 5, let's say, directions. Of course, I don't have time to go in the details of all of them. I will try to give some spot contribution, and in case you could ask me later on a few questions to deepen some of them. So the first contribution is related to malware, because malware has been one of the, let's say, entry point to compromise the security of industrial control systems. In particular, we read of them on newspapers. Usually malware is the door that basically is used to deploy some malicious activity and compromise and possibly also block the operativity of an industrial control system. We developed novel techniques to classify and detect malware based on abstract interpretation, for example, and also some other based on machine learning and deep learning. In particular, in this work, we deployed many different classifiers based on a quite large different number of features, including static analysis, dynamic analysis, and also hybrid analysis features on different level of granularities, and applying many different classifiers to study how they behave when on the task of classifying and detecting malware, including traditional machine learning and also novel deep learning algorithms. Another approach that has been investigated is related to the privacy of data, especially when the industrial IoT devices connect to the internet, for example, to interoperate with smart contracts that are deployed on public blockchains. In fact, when data are delivered to public blockchains, they are kind of public, and this might violate privacy and confidentiality issues. To study this problem, we developed novel static analysis algorithms that have been deployed on public blockchain. In particular, we used Tendermint, which is an open source blockchain for which we develop a smart contract layer based on a subset of Java, which is deterministic, which is important for blockchain and smart contracts. And we started developing static analysis to verify security posture of these smart contracts. Moreover, we develop also techniques based on dynamic analysis of smart contracts, where we deploy a society of different bots, where each bot plays a different role in the smart contract. For example, different users. You might think of a buyer, of a seller, or depending on the contract, there might be different roles. And these bots actually interact with the contract in order to exercise the contract and reveal potential problems. One particular activity that has been conducted and is important for cybersecurity is a particular analysis related to a device, a smart robot. We took a collaborative robot and we did some penetration testing on this robot to verify whether any vulnerabilities was present or any defect was present in the robot that could open the door for a cyber attack. This activity was supposed to analyze and reveal if any, let's say, outdated software was running on the robot for which some vulnerabilities are known, or if any obsolete and old cryptographic libraries could be used in the robot for which some exploits are available. The activity was conducted with some, let's say, interesting results. I will cite just a couple of them. One is a successful attack where we could steal the credentials used to control the robot, because we analyzed the network traffic that was exchanged between the robot and the control unit, which was unclear, and the password was protected with a very simple algorithm that we could reverse. The second attack that we could mount on the robot was a tampering attack. Basically, we could tamper with the program running on the robot. And what we could do, we could change the speed of the actuators, of the motors. Basically, potentially causing damages to the robot or to the, let's say, to the final product at which the robot was working at. A last activity that we conducted was related to protecting, let's say, the software running on IoT devices from attacks known as man-in-the-end attack that are meant to tamper with software that is running on the robot, and in general on software running on devices. We basically define brand new techniques meant to protect against man-in-the-end attack. And we run some, let's say, experiments with users. They are, let's say, human experiment where we ask some people to try and mount attacks, and we evaluated whether the countermeasures were effective in blocking these attacks. A number of publications have been, let's say, released and published after these to document and disseminate the result of the research on journals and on conference. I could mention one of it, the last one at this page, which was let's say, not the last one, but the one before the last one, which has been published in the POPL conference, which is one of the most prominent conferences in the field. And another conference publication, which is the one before the last one at this page, which was awarded the Best Paper Award at the corresponding conference, which is a very interesting result to us. And now I'm open to take your questions.
Very good, Mariano. Questions about this layer of the stack that we are building on top of the HiSlab? If there are no questions, no problem. Okay, this means that you've been very clear. Thank you, Mariano. So
I have then one question.
Okay,
so there was the talk by Massimo Mero on the CPS security, right?
Mm-hmm.
And this is on software security, and I'm just wondering what kind of interactions or collaborations you have with that part of the project.
Let's say they are two approaches that apply to different levels. We, of course, collaborate. I think that Massimo is also author of some of these papers. The idea is to, let's say, fill the gap and develop a holistic approach that takes into account both the work that Massimo presented and the work that I just presented on application security. But so far, let's say, we didn't achieve, let's say, a unifying result that consider both of the contributions.
Okay.
Okay. Thank you very much. So we can move to the next speaker, Alessandro Farinelli, about mobile robots. So Alessandro, take the control.
Hi, good afternoon, everyone. Can you see the screen correctly?
Perfect.
Okay. So I am Alessandro Farinelli, and the presentation will cover the research and implementation activity related to mobile robots. The main idea is to present the work that has been done on trying to, let's say, implement the high-level actions that we need with to perform with the mobile robots in a smart factory environment. And this is mainly related to the common trend that we can see for the use of mobile robots in the smart factory, which is essentially to build collaborative mobile robots that share the workspace with the human, and so needs to be reactive to unexpected events and needs to have high-level cognitive capabilities to assist the human in the activity. I will go a little bit more in detail in this particular. I will present 3 research lines very briefly. I will go a little bit more in detail for this one because it's the one that has been actually implemented on the mobile robots, on the Kairos that are in the ICE lab. And the problem that we are addressing here is a multi-agent pickup and delivery problem, where robots need to coordinate to deliver a set of items to a set of locations. This is a well-known problem in the literature, and in our case, the way we spin this problem is that we don't focus on a single item to be picked up and delivered, but each robot can bring more items in one single trip, which complicates the problem from the, let's say, from the combinatorial point of view, because the robot should stop in different stations. And the goal here is to guarantee that the robots can have can find the conflict-free paths, even in face of possible mobility issues that they can have. So it's difficult to say exactly how long a robot will take to complete a path, but you still want to have conflict-free paths. What you see in this video is the topological graph that is underlying the movements of the robots. And what you see here is a simulation of the robots picking up different items and then moving in the environment to leave the different items, to bring the different items to the different stations. The interesting part is that this is a very complex combinatorial optimization problems. And of course, you have to address the trade-off between finding good solutions, but also having a tractable problem. And the way we are dealing with this is to compare a solution that we are proposing, which is based only on the coupling, essentially the path planning part, with a full multi-agent coordination approach, which is guaranteed to find the optimal, but is intractable in most of the cases. The interesting part is also that the robots are synchronized, so you can see that they synchronize their movement. This is very important because, as I said before, it's difficult to do a time-based planning of the different actions of the robot, because you can very often have delays in the way the robot moves. The next research line is related to planning, so planning high-level control for robotics platforms. In this case, the main focus of the activities has been to use high-level planning approach. In particular, in this case, we are focusing on one approach, which is called the partially observable Monte Carlo planning, which is an approximate solution for a general framework, which is the partially observable Markov decision process. And in this case, what you see here in the video is a velocity regulation problem where the robot has to decide at which speed to proceed, so to make sure to avoid obstacles, but also complete the path as soon as possible. The key insight here is how you insert previous knowledge into the planning part. so to make sure that the robots can exploit as much information as possible on the environment. In this case, the information that we can insert is similarity in difficulties of traversing the path with respect to the different segments. The research results that you see here are related to this research line, and some of them are also related to the adaptation side, which is using reinforcement learning to perform mapless navigation. The last research line is related more to the monitoring and anomaly detection for mobile robot behaviors. In this case, the idea is to look at the robot as a generator, so to say, of time series data, and to analyze this time series data with different techniques. We do use standard techniques such as, for example, hidden Markov models to try to understand what is an anomalous situation and what is a nominal situation. And we are also moving towards our, let's say, more advanced and interesting approach, which is based on satisfiability modulo theory. So essentially, we are trying to synthesize rules that defines what is a nominal situation based on execution traces of the intelligent systems. So this is what you see in the right. Essentially, behind this, there is, again, a partially observable Monte Carlo planning execution of a specific robotic task, which is actually the velocity regulation we've seen before. The user can specify some rule templates that should be met by the robot, and then by solving a max SMT problem, the system tells you which are the rules that has been violated and which are the rules that actually are conform with the specification of the user. And this can be an interactive process where the user can refine rules if it sees that some of these rules are always violated by the system, for example. This is from here onwards, I will go a little bit more fast. This is the two mobile robots that we have in the ICE lab. These are the components of the robot. So each of the robots is actually quite complex system with several sensors and actuators. And this is the basic software stack which compose the robots. Let me go directly to the implementation results, which are the most important implementation results that we achieved. The first one is the setup and test of the basic functionalities of the two platforms, which is essentially, well, teleoperation, safety features, autonomous navigation, localization, and SLAM. And this is essentially using the basic software that comes with the robot. Then we have the integration of the robotic platforms with the ICE infrastructure, which has been shown also at the beginning of during the demo. And also we also implemented multi-robot coordination on the two platforms, which was not easy because these robots are not designed to do multi-robot coordination from the start. But we managed to implement the methods that I briefly explained before actually on the two robotic platforms. So this is a video showing the robot moving and localizing on the ICE lab. And as you can see, what you see here is essentially what the robot perceives and how it localizes in the map. This is a pickup and delivery specific task executed by the robot. Here, I will not go on until the end, but the interesting part is that each of these actions requires activation of a set of quite complex software stack. And one part of the next work that we would like to do is to actually make this task more efficient, intervening at the lower level of having a lower level integration with the robotic software. What you can see here is that the robot picked up two pieces, and now it will dispose the two objects inside this bin. And the interesting part is that all this task has been executed in complete autonomy. The last part is the multi-robot version. So in this case, what you see are the two robots moving in the environment. And on the right, you see a representation of what they're trying to do. Essentially, you can see now that the first robot is going to the pickup location. And in this case, we don't execute the pickup. We just reach the location and then consider the task to be done. And then the other robot moves to the pickup location while the other is going to the delivery. The interesting part here is that what you can see now that the two robots are actually synchronized. So you can see that one robot is stopped to let the other pass, and then we move to the other, to the delivery location and come back, always using a conflict-free path, which is what we wanted to achieve from the start. Then the robots will complete the path, and as you can see, it will of course avoid going through the vertex which is occupied by the other robot. This is a very brief summary of the research results, which are to some extent related to the different lines that I presented, and this concludes the presentation. If you have questions or clarifications.
Okay, I have one then. I think it's an interesting talk. I think the problem of multi-robots delivering multi-objects in an optimal way may be very interesting problem, but it's NP hard problem maybe. So I don't know whether you talked about your approach, but can you just briefly introduce the approach you are taking for that problem? Yeah.
Yes. So thanks for the question. So maybe the best is to show here. What happens is that, what happens is that, as you correctly say, the multi-robot, even the single item multi-robot pickup and delivery problem is NP hard. So the way we address this problem is that we essentially do a decoupled solution where we have a fixed order. The first robot plans a path as if the other don't exist. The second robot tries to adapt to the path of the first robot, and so on until the last one. This, of course, does not guarantee that you can always find a solution, otherwise the problem would not be NP hard. But the interesting part is that in this case, we can combine pathfinding, which is defined as you start from one position, you have to end up in another given position, with task assignment. So we can switch tasks so to make sure that the path that the robots find are actually conflict-free. Even this is not enough, so we can guarantee that these are conflict-free paths, given some assumption on the topology of the map, which essentially is milder with respect to the assumption that were made in the past. And this assumption is that every robot can reach the goal position without traversing on another robot's home position. So if you have this guarantee, then our approach guarantees to find conflict-free paths.
Okay, thank you. Thank you. Yeah.
Okay.
So I have a quick question. So I really liked the talk, and especially the videos that you showed. In the last video, you said that the two robots are synchronized with each other. So can you maybe clarify a little bit as to what you mean by that? And also, are the robots equipped with some cameras, or what is the meaning of synchronized?
Yes, so the way they perceive the environment is with two LiDAR rangefinders and an RGB camera in front. So that's the way they perceive the environment. But then they transmit to each other their position. They are both localized in the same frame of reference, and they transmit to each other their position. And when I say that they are synchronized, what I mean is that during the whole execution, they keep on passing a token, like in a round robin. So they pass the token one to the other. And they always say, this is my path. This is where I'm going. This is where I am. And so if one robot knows that another is occupying a vertex that he should go through, he knows the path, so he knows how much to wait until it can actually move and find a free path.
Understood. So then if the robots are equipped with these cameras and rangefinders and so on, then what is the necessity, or then if I do not have this additional requirement of each robot knowing the local position and having the same frame of reference, then how much is the loss in performance, or how difficult? Of course, the problem is then more difficult, but is it like more doable? Is it still doable? Because that would be a more general setting.
That's very true. The biggest problem, if you remove the, let's say, so essentially, more or less what you're saying is that they don't need to communicate because they can perceive one another. This is true. The big problem with this is that the observation that they can have is limited both in range and in how much semantic information you can extract. So obviously they can avoid each other as obstacles, but if one wants to go to the position of the others, this would be a situation where only using perception and without having a higher level of communication, you will not be able to solve, because they will keep on avoiding each other without understanding what they should be doing to finalize their goal. So it would be much more harder, and I don't think you can guarantee the conflict-free paths that we can guarantee now.
But given that in this environment there would also be human beings walking, and there could be things getting shifted all the time, so how do you still guarantee that assumption of the common frame of reference and so on?
That's a very good point. And actually, for what concerns localizations, we don't we assume that you can localize because we have a known map, so you should be able to understand if there are new obstacles. But for what concerns the other point, which is, of course, you don't have control over humans, you just have to react. This is something that we are working on at the moment. And essentially what we're working on is path replanning. So you plan a path, but then there is a part of the graph that is obstructed, could be edge or could be a vertex, and you have to replan the path around the obstacle. So in this case, we just react and we get whatever we get, because obviously you cannot coordinate, at least we're not at the level where you can coordinate with the human.
Understood. Thank you very much.
One last question or comment. When I visited the ICE lab last time, I think it's you or somebody else told us that for the robot to build a map, glass window or glass is a problem. So did you solve the problem? Glass means that I think the LiDAR or whatever penetrates the glass. So
yes, okay, yes, because there were glasses on this side of the map. Yeah, that's true. Now this problem has been solved. Essentially because at the level of the laser, there is always obstacles that you can see, and the only part where you don't see the obstacles are the glasses. And so now we've been able to solve that part. But this was just using the basic software of the robots. So this was
okay. Thank you. Yeah.
No problem.
Okay. Very good. So let's now move from the mobile robots to collaborative robotics. So Riccardo Moradore, you can take the control of the screen.
Okay. Okay, so you should see the presentation. So good morning or good evening to you. So this talk is about initial activity on the cobot, so on the collaborative robot that we have in our lab. As you know, collaborative robotics is one of the key ingredients of the Industry 4.0, and there is a sort of change of paradigm. So instead of having robots behind a cage, then we have a robot that are actually working with people. So in this sense, we have to tackle these three problems that I highlighted here in a slightly different way. So for sure, we need to have position accuracy when the robot is moving in free motion, but the behavior of the robot must be compliant anytime the end effect of the robot interact with the environment. And another key requirement is that we must guarantee the safety of humans. So anytime the robot is interacting with people, if the interaction is not as expected, then some security measure should be activated. So these are actually the challenges behind collaborative robotics. So we have to assist the human operator over the whole procedure. So actually we have to understand the tasks. So here the problem of knowledge representation that Paolo discussed an hour ago is actually playing a very big role. And then we have also to manage all the uncertainty that are affecting the system, so human motion, unstructured environment, and disturbances. Then we move actually on, instead of having hardware in the loop, we actually have the human in the loop. That is something that is actually much more uncertain. Then another challenge that we must face is the learning by demonstration, and also the estimation of the human intention in a sort of very reliable way to help the human over the procedure. And only if we actually manage to tackle all these challenges, we can guarantee that the collaborative robotics should improve efficiency, flexibility, and safety. I think that is worth highlighting that most of the topic about collaborative robotics are, in a sense or in another, part of the program of several courses in our new master degree in computer engineering for robotics and smart industry. So there are actually the competences that we already have in ICE actually. So most of them actually we had in the Altair lab in our department, and that we moved in the new lab. So you know how to design variable impedance or admittance control. Of course, we adapted this design on the particular task of collaborative robotics. So like tools handover, lifting heavy object, task sharing, and so on. Then we know how to program in an effective way robots, for example, using ROS, the ROS framework that allows us to actually improve the basic functionality that the manufacturer provide. Then and then we can integrate also new algorithm based actually on AI or machine learning tools to estimate the human intention, to estimate the phase of the task, and so to properly react and to properly support the operator. So in this part, actually, we have to integrate a lot of competencies coming from robotics, computer vision, AI, and so on. About the implementation, we actually, in the last year, we integrate identification methods for estimated the dynamic parameters of the cooperative robots that we have in our lab. So in particular, the ABB Yumi and the Universal Robot UR5, because even if these robots are quite popular, actually the manufacturer doesn't provide accurate estimates of the parameters of the dynamical model. So you cannot use such model in a reliable way. So you have to identify their model. And actually, it turned out that we have not only to identify the model of the robot, but also to, I would say, reverse, to estimate the controller, because both the ABB and the UR5 robots, you can use this robot only using the position control algorithm or the velocity control algorithm. So you cannot bypass such a controller. And the manufacturer did not provide the parameters for the controller. So actually, one thing that we had to do was to identify also the not only the dynamic model of the robot, but also the controller. And when we have all this information, then we implemented passivity-based teleoperation algorithm. And also we were able to also model the system using stochastic methods. Then we also had to integrate computer vision tools like calibration method, and more important, the 3D reconstruction of the environment. And we also have some experience on the 3D thermal reconstruction, so using thermal camera instead of standard cameras. And then we also started to integrate, as I said, machine learning algorithm with a supervisory control architecture in order to implement a very effective visual servoing control and also collisional avoidance algorithm. So these are actually what we are working in these days on the cobot that we have in our lab. So these are just a list of papers that I don't want to spend time, but the only thing that I would like to mention is that in most of these papers there is the word surgery, because actually we are bringing all the knowledge and experience that we gained in implementing autonomy in the surgical scenario in the industrial scenario, because some of the challenges are common. So, and we gain, I mean, a lot of experience. And as you know, one of the definitions of experience is what you get when you don't get what you want. So actually, we gain a lot of experience in the surgical scenario that we can exploit also in the industrial scenarios. And that's it for my side. So if you have any question, please, I'm here to try to reply.
Okay.
I like to have one comment because after your talk, I have to excuse because my other schedule today. So I think IC Lab is really a great asset for your program. I hope that this IC Lab can be a platform for not only research but also education. So the master program and the IC Lab have some good close what the link, so that students can have project to carry out as part of the requirements of master degree or that kind of thing. So I think if that's happening, then I think this program will be successful both in research, also in education. This is just comment. I'm impressed with the progress that you have for IC Lab during the past year. So this can lead to more closer relationship with also local industries or other industries to have some research collaboration with you, but also the educational part, the boosting educational program, so that students can have real experience in your IC Lab in Industry 4.0 environment. Anyway, that's my comment. I think yeah, that's all right. So I would like to excuse. Thank you. Yeah. So
it's okay. So if there are no specific questions, let me move to the last presentation about vision technology and mixed reality. So let me ask to Francesco Setti to take the control.
I'm sorry. So let me share the screen. Okay. Okay. So can you see the screen? Yes.
Yes, yes.
Okay, sorry for the noise. So I'm going to present the visual technologies and mixed reality part of the project. Is quite a big part. Indeed, we have 4 main topics into that. I promise I'll be as quick as possible. And
5 minutes, no more.
yes, I know. So I said we have 4 main topics. One is quality control. One is related to visual monitoring of the environment. And then we have digital design related to 3D printing. And finally, mixed reality and augmented reality interaction with robots and devices. So let me start with the the goals of the whole project, which is about tracking people and robots together in the environment, perform quality control with advanced techniques and advanced technologies, do activity interaction monitoring and prediction of humans mostly, and then virtual and mixed reality. Sorry again. What about the quality control part? We have a lot of devices and instruments. We have 3D scanners, we have smart cameras, but our main focus is related to shape reconstruction with multi-camera systems, surface analysis, both with cameras and scanners like atomic force microscopes. And this is a work we do together with the physics lab in our department. And we are also doing some preliminary work on the usage of deep learning for quality control in steel and in other material, where the problem is not just to say if the product is good or not, but also to localize and explain why it's good or not. So, in the visual inspection part, we are also very active in the lighting technologies for analyzing surfaces, and also for 2D and 3D characterization of surfaces and textures. We developed quite a lot of code. Most of them is publicly released in GitHub, and of course you are free to use it for your work if you're interested. And we have also quite a lot of publication in this topic. The second main topic is visual monitoring of human activities. We take advantage of our previous works in interaction, human interaction and human behavior analysis we did in the past, and we are moving it towards the working environment. The main focus is on people tracking and also trajectory prediction. This is an important topic for human-robot cooperation, human-robot interaction, especially when AVGs and mobile robots are involved, and also for human body modeling. Again, we developed quite a lot of code based on the last, very last implementations of the transformer networks, and it's also available for research in GitHub. The third topic is mixed reality and augmented reality. We are using HoloLens, Oculus Rift, Vive, and other devices for developing training environments where people can understand how machines, like you see in the video. In the upper right video, you see a cockpit, and this is an airplane cockpit where the user can do training, of course, preliminary training, and understand how everything works in a virtual environment. This is a work we are doing together with a company located in Italy, and is also there is extension of this project for the ESA, so for spatial activities, early training of spatial activities. And the last part is about gesture-based interaction with robots and systems in general. And it's so gesture recognition mostly. Again, there is quite a lot of code, but also here I would mention we did we performed a 3D model of the ICE lab. It's quite almost complete 3D model of the ICE lab, and this will allow us to generate also virtual reality and mixed reality interactive visits, and also to do this is very helpful for other tasks like navigation. So having a 3D model of the whole environment can be beneficial for AGVs and other tasks as well, other technologies we saw earlier today. Okay, and the fourth pillar of this presentation is about digital design for 3D printing. We have 2 3D printers, and we are doing a lot of work in geometry. This is not my own work, so I'm sorry if I won't be very specific on that. But the main goal here is to create and acquire printable models, so geometry analysis and generation for printable models. Decompose the objects into parts and optimize the printing in order to minimize supports and minimize the post-processing of the material and the product itself. And also an important part is simulating material appearance and mechanical properties. For mechanical properties, of course, is more related to the material itself, but also the geometry has an effect. And for the appearance, this is a big part in 3D printing, because many times we want to simulate actually materials that cannot be printed in 3D. And so this is quite an important point for industry. And we are also working on simulating artistic design with volumetric packing, which means basically to optimize also the shapes in order to be more similar to what humans will design. And last but not least, we have methods for surface analysis and remeshing. So once we design the general shape of an object, we want to do decoration mostly, and for many cases, and we need to do a very accurate geometric representation. So remeshing the surfaces in order to do modification, like fine modifications of the wall geometry, and do decoration of the object itself. Okay, I think I've been quite quick. This is a small recap of the implementation results of all the current methods, and this is again another list of publications. Am I in the 5 minutes, Franco?
More or less. Okay, it's okay, it's okay.
Okay, so, sorry.
I don't know if there are questions. Okay, if there are no questions, okay, we just arrived at the end of all presentations. So I don't know if you like to say something now, or if you probably would like to take the time the next days and then prepare the report that every year we are asking for. Let me know.
Yeah, I think that probably Samarjit, we may want to organize a call so that we can discuss. Unfortunately, I saw only part of the presentation, so right now it would be difficult for me to give a complete assessment. What I've seen is pretty good. Now, one of the key issues that we talk about in the previous report is to show collaboration across different research areas, and that we will have to see how that was accomplished, because it's important that there is a cross-fertilization of the different areas and people working together in different domains, because only then you can really get a superior result.
Very good. Okay, so
I just want to say, a few sentences. So first of all, I think I was really, and I think everyone was really very impressed by what you have accomplished in that ICE lab. And also thanks to Franco and everybody else involved to give such a professional looking demonstration, right? So I think that was extremely impressive. And also in terms of everything that I have heard, I think there is really very high quality research that is going on. And also in terms of research output, I'm very, very impressed. So I, as Alberto already said, I would have also expected a little bit on how the different parts are getting connected to each other. Like, for example, there is CPS security, software security, there is data collection that has implications on many different aspects. So maybe there is already collaboration going on, and some of the people have said that, but it would also be a good idea to more explicitly highlight that and see how everything is coming together, and also how probably everything is really, I would say, making use or benefiting from the excellent ICE lab infrastructure that is there. So that is all I could say sort of immediately after looking at this presentation. But I think overall, this is a very, very impressive project and very impressive progress.
okay, thanks a lot, Samarjit. So we will wait for your report to use it to go on in this fourth year, okay, with the target that that we reported in the stuff. If you need some other information, feel free to contact me, okay? And thanks you very much for your time and for this pretty long and hyper compressed workshop. Okay, have a good day, night, evening, and so on. Okay.
No, I mean, I have enjoyed it as much as I had enjoyed the last workshop. I also enjoyed very much this workshop, and more than a reviewer, I think it was also very educative for me myself. Thank you very much.
Thank you. Okay.
Indeed, I would like to join into this. I mean, it's too bad that we couldn't have done this in person. I really like Verona and visiting you. So next time I hope to be able to see you in person.
We will do for sure. We will organize for sure.
Well, I'm being vaccinated.
Okay.
So in a week, I will be free to travel. So keep this in mind. Okay.
But vaccinated does not mean that you will still not infect. Vaccinated means that you are protected.
But I don't care. Sorry to say at this point. No, I'm kidding. Of course I do. Of course I do.
Bye. Have a nice evening.
Good night, everybody.
Bye. Thank you.
Ciao, Paolo. Ciao, Franco.
Ciao, Alberto.